Section 4.9, example 2. A 2 kilogram mass is attached to a spring with stiffness of 40 Newton per meter. The damping constant for the system is 8 square root of 8 square root of 5 Newton second per meter. If the mass is pulled 10 centimeters to the right at the equilibrium and given an initial leftward velocity of 2 meters per second, what is the maximum displacement from equilibrium that it will attain? So first of all, we have to solve a differential equation that in general form is given by m y double prime plus by prime plus ky equals to 0. It is important to state that, or recall that k is the spring constant and b is the damping coefficient. B damping coefficient, k spring constant. So in this particular case, m takes the value of 2 kilograms, b equals to 8 square root of 5 Newton seconds per meter, and k is equal to 40. We have to find y of t because we have to find the maximum displacement. So once we find y of t, we're going to find the maximum displacement. Also, notice that we have a condition that the mass is pulled 10 centimeters to the right of the equilibrium. So that is equivalent to y at 0 equals to 10 centimeters or equal to 0.1, so that we have the same kind of unit, so meters. We know the acceleration or velocity is the derivative of the distance. So the velocity, which is the derivative of y, is going to be 2 meters per second. So the equation is going to take this form: 2y double prime plus 8 square root of 5 y prime plus 40y equal to 0. And now we're going to solve that equation to get the value of y. Now, recall we can use the auxiliary equation since the differential equation is homogeneous, 0 on the right. So we have this new equation. And then we are going to rewrite it. We can divide everything by 2. So we have r squared plus 4 square root of 5r plus 20 is equal to 0. And then using the quadratic formula, we have r equals to negative 4 square root of 5 plus or minus 4 square root of 5 squared minus 4 times 2 times 20 divided by 2 times 2, or just 2, because we have simplified the equation, the quadratic equation, then the number in front of r squared is 1. So that is why we have a 1. So simplifying this, we have negative 4 square root of 5 plus or minus square root of 80 minus 80 divided by 2. And this produces negative 2 square root of 5, which is a double real solution. Okay, so recall when we have a double real solution, the solution is going to be the form y of t equals to c1 plus c2 t e to r t. So in this case, y of t is going to be c1 plus c2 t e to negative 2 square root of 5t. Then we're given two conditions. The conditions of the initial value problem, which are the one I'm shading now in blue. Y of 0 is equal to 0.1 meters, and y prime at 0 is 2 meters per second. So we have that y at 0 is equal to c1 plus 0, because when we replace t by 0, c2 is going to be 0 times 1, because the exponential is going to be e to the 0, and that's going to be equal to 0.1. So in this case, c1 is 0.1. Now, to find the value of c2, we have to differentiate, and for this reason, we have to find, or we have to apply the product rule, derivative of the first and the second, plus derivative of the second and the first. So we have c2 e to negative 2 square root of 5t minus 2 square root of 5 e to negative 2 square root of 5t times the parentheses. Again, derivative of the first times the second, plus derivative of the second times the first. So we have that y prime at 0 is going to be equal to c2 times 1, because the exponential is going to be e to the 0, that's going to be 1, minus 2 square root of 5 times 1, which is the exponential, times 0.1 plus c plus 0, Then, if we isolate, well, this is equal to 2. Then, if we isolate c2, c2 is going to be equal to 2 plus 0.2 square root of 5. Because remember, when we multiply negative 2 square root of 5 times 0.1 is going to produce the 0.2 square root of 5. So we continue, and then our function is going to have the form, our solution of the differential equation is going to have this form, 0.1 plus 2 plus 0.2 square root of 5 t times e to negative 2 square root of 5t. This is, in fact, the solution of the differential equation. Actually, it is the solution of the initial value problem, indeed. Solution of the initial value problem, and this is y of t is the same as displacement. Okay, so now we have to, the problem is asking to find the maximum. To find the maximum, we have to find the first derivative of this solution, the same as we did in calculus 1 when we were looking for critical numbers to find relative or local extrema. So we have to apply again the product rule. Derivative of the first is 2 plus 0.2 square root of 5 times the exponential, derivative of the first times the second, plus derivative of the second. The second is the exponential, so derivative of the exponential is going to be 2 square root of 5 times e to negative 2 square root of 5t times the first, which is 0.1 plus 2 plus 0.2 square root of 5 t. And then now we're going to find the maximum. Remember, the maximum is when y prime of t is 0. So we need to equal the expression we found for the derivative. We equal it to 0. So something we can do is factor the exponential, because the exponential is never going to be 0. So we factor the exponential, we're going to have 2 plus 0.2 square root of 5 minus 2. So let me do this again. It is 2 plus 0.2 square root of 5 minus let me see. Yeah, when you multiply, these 2 times 0.1, that's going to produce 0.2 square root of 5. This multiplication is going to produce a negative 0.2 square root of 5 minus 2 square root of 5 times the parentheses, which is 2 plus 0.2 square root of 5 times t. And that should be equal to 0. So these two things cancel, which are the same with the same different exponent. So we have two new expression, which is e to negative 2 square root of 5 t times 2 minus 2 square root of 5, 2 plus 0.2 square root of 5 t equal to 0. Remember, the exponential is never equal to 0. So the other thing is going to be what is equal to 0. So we have 2 minus 2 square root of 5 times 2 plus 0.2 square root of 5 times t, and that is what must be equal to 0. So we have that we move the 2 to the other side, and it's going to move negative, and with this negative everything's going to be positive, and then distribute this number outside. So we're going to have what? We're going to have 4 square root of 5 plus 2. Okay, this is this t is multiplying. Okay, here this parenthesis goes here, and then this t multiplies the whole thing. Okay, so we have 4 square root of 5 plus 2 times t equals to 2. And now we isolate 2. 2 is going to be 2 over 4 square root of 5 plus 2. And these also can be simplified as 1 divided by 2 square root of 5 plus 1. And then if you compute it in a calculator, it's going to be around 0.18. 0.18. Also, you have to make sure that 0.18 is in fact, and that at 0.18 you have in fact a maximum. So how do you do that? Remember, this is a critical number from calculus 1. So we have to test, and then you have to replace a number to the left of 0.18 and a number to the right of 0.18 in the derivative. When you do that, you're going to have positive and negative. So you can pick, for example, t equals to 0.1 and t equals to 1. So y prime at 0.1 is going to produce a positive number. Y prime at 1 is going to produce a negative number. So that is why we have, in fact, a maximum. So at t equal to 0.18, a maximum occurs. And then to find the maximum displacement, which is what the question is asking about, the maximum displacement is going to be given by replacing in the solution in the actual solution 0.18. So that will be in the actual function, you replace 0.18, so that will be 0.1 plus 2 plus 0.2 square root of 5 times 0.18 times the exponential, which is e to the negative 2 square root of 5 times t, but t happens to be 0.18. So what we did here is to, in the function we found in the solution of the initial value problem, in this solution, the one that I'm highlighting now in pink, you have to replace the value of t where the maximum occurs, and that t we found to be 0.18. So it's in this function where you replace t by 0.18, and that is going to give you a value of y will be 0.24 meters. So responding to the question was what is the maximum displacement from equilibrium that it will be attained? What is the maximum displacement from equilibrium that it will attain? So the maximum is 0.24. And this concludes the solution.